In this lesson, we'll learn about some additional properties of intervals. By the end of this lesson, you should be able to invert intervals, to identify and write compound intervals, and you'll learn some other tidbits of interest about intervals. In the previous lesson, I encouraged you to memorize intervals as white note pairs, and I said that you only need to memorize seconds, thirds, and fourths. The reason you only need to memorize those three sizes is that you can derive the larger intervals from those pairs if you understand the concept of interval inversion. In a nutshell, if you read a note pair backwards, you get the inversion of that interval. C to E is a major third, and if you read it backwards, you get a minor sixth, E to C. Looking at the staff, you'll notice that an interval and its inversion divide an octave into two parts. The easiest way to think about inverting intervals is to take the top note and transpose it down an octave, or to take the bottom note and transpose it up an octave. Here's a visual representation. In the first instance, we have a major third, D to F sharp. If we move the D up an octave, the result is a minor sixth. In the second instance, we have an augmented fourth, G to C sharp. If we take the G up an octave, the result is a diminished fifth. In the last instance, we have a perfect fourth, E to A. If we raise the E an octave, the result is a perfect fifth. While these examples are all harmonic intervals, that is, the two notes sound simultaneously, both harmonic and melodic intervals can be inverted. You may have noticed that when you invert an interval, both the size and quality change. The size of an interval and its inversion will always sum to 9. Fifths invert to fourths, thirds invert to sixths, and vice versa. The quality also changes. If you start with a major interval, the inversion will be minor and vice versa. If you start with a diminished interval, the inversion will be augmented and vice versa. Perfect intervals are the exception. Perfect always inverts to perfect. If you want to double check your work, the number of semitones in the starting interval plus the number of semitones in its inversion will always add up to 12. Taking the intervals from the previous slide as our examples, a major third inverts to a minor sixth. A major third comprises 4 semitones, and a minor sixth comprises 8 semitones, totaling 12. An augmented fourth contains 6 semitones, and it inverts to a diminished fifth, which also contains 6 semitones for a total of 12. Incidentally, this pair of intervals, the augmented fourth and diminished fifth, is a bit of a special case, and I'll have more to say about them closer to the end of the lesson. A perfect fifth, which consists of 7 semitones, inverts to a perfect fourth, which consists of 5 semitones, for a total of 12. Here are those same intervals and their inversions in staff notation. Here's a marvelous example of intervals and their inversions in real music. The example comes from the opening of the first movement of Brahms's Fourth Symphony. Take a minute to find a recording of it on YouTube or through one of the library's streaming sites and listening to this opening a couple of times, or play it on the piano. If we look at the melodic intervals between the slurred notes, we see basically an alternating pattern of thirds and sixths, with a couple of perfect octaves thrown in for good measure. The thirds are a mix of major and minor, and the sixths are both minor. I've indicated the melodic intervals across the rests above the staff. From the G in measure 1 to the E in measure 1 is a minor third, for example. You'll notice that most of these intervals are also thirds, with one perfect fourth thrown in the mix. Looking at the material this way, it appears as though Brahms has composed his melody in such a way that it's saturated with different kinds of thirds. This repeated use of the same interval provides cohesion to the theme. We hear a similar sound reiterated over and over again. But if we look a bit deeper, we realize that sixths are simply inversions of thirds. I've highlighted in red the sixth in the melody. What if we consider the inversions of these intervals? Well, the minor sixth EC inverts to the major third CE, and the minor sixth D sharp B inverts to the major third B D sharp. If we rearrange these a bit on the staff, it's revealed an interesting property of Brahms's melody. The melody breaks up neatly into two halves. The first half consists of a descending chain of thirds, and the second half consists of an ascending chain of thirds. The two halves are separated by the perfect fourth. Listen to the melody again and see if you can hear the descending and ascending chain. The second main topic in this lesson is compound intervals. Simply put, compound intervals are any interval that is larger than an octave. You'll notice that all of the intervals we've talked about up to this point have been smaller than an octave, with the exception of the one harmonic interval in Schubert's Haydn-Rost line that I pointed out in the last lesson. I'll revisit that example in a moment. We don't really have fancy names for these intervals. Ninths and tenths are common enough that we refer to them as such. A ninth can be major or minor and consists of an octave plus some kind of second. A tenth can also be major or minor and consists of an octave plus some kind of third. The quality of the second or third determines the quality of the ninth or tenth, respectively. For intervals larger than a tenth, we typically refer to them as either an octave plus a fourth or a compound fourth. More often than not, though, compound intervals are reduced to their simple equivalent. Simple intervals are those that span less than an octave. Here's the Schubert example again. I've circled the interval between the bass note and the voice on the downbeat of every measure, and I've labeled them below the staff. Our last topic concerns enharmonic intervals. I mentioned earlier in the lesson that the augmented fourth diminished fifth pair is unusual because both of them consist of 6 semitones. If you think about it, when you play two notes that are 6 half steps apart on the piano, they're going to sound the same whether they're spelled as an augmented fourth or a diminished fifth. If you play F to B on the piano or B to F on the piano, it's going to have a very similar sound to it. Perhaps a better example would be to play G to C sharp, an augmented fourth, and G to D flat, a diminished fifth. Because it's difficult to tell them apart simply by listening to them, these two intervals often go by the singular name of tritone. The name, which means 3 steps, encapsulates the ambiguity encountered when hearing these intervals. Just as we had enharmonically equivalent pitches that sound the same but are spelled differently, we can have enharmonically equivalent intervals as well. These are intervals that sound the same but are spelled differently. A major third sounds just like a diminished fourth, but they appear different on paper. A minor second and an augmented unison will sound the same, but they appear different on paper. We've actually already studied this distinction. It's the difference between a diatonic and chromatic half step, as you can see on the right side of the slide. A brief aside, the tritone actually has a very interesting history. Because it consists of 6 half steps, which was considered an unholy number, and it sounds unpleasant or dissonant, it was actually banned for a long time by the Catholic Church during the Middle Ages and early Renaissance. They called it the devil in music. That brings us nicely into our final topic, which is consonance and dissonance. This concept applies particularly to harmonic intervals. Intervals that sound pleasing are consonances, and intervals that sound unstable or unpleasant are dissonances. There are several factors that contribute to the perception of consonance and dissonance, some of which are mathematical and scientific, others of which are more a matter of interpretation. From a mathematical point of view, simple frequency ratios produce consonances. For example, the orchestra tunes to an A that vibrates at 440 cycles per second. There is another A, an octave above that, which vibrates at 880 cycles per second. This results in a 2-to-1 frequency ratio and a perfect consonant interval. You can see I've listed some other common ratios, simple ratios like 2-to-1 for the octave and 3-to-2 for the fifth. More complex ratios are things like 128 to 81 or 62,258 to 347. And I don't really want to get into ratios and proportions too deeply here. However, if you're interested in this kind of thing, I would encourage you to watch Donald Duck in Mathmagic Land. And I'm serious about this. I've put a link to it on Canvas. The video is a great introduction to some fundamental mathematical properties of music, art, and architecture, and, incidentally, was my introduction to music theory way back when I was in 3rd grade. We can classify the intervals we've learned so far into consonances and dissonances. Bear in mind that these classifications are by no means universal. They tend to apply to Western art music written between 1600 and 1900. Among the consonant intervals, we can speak of those that have simple frequency ratios as being perfect consonances. Not surprisingly, perfect unisons, octaves, and fifths appear in this category, and the fourth is conspicuously absent. Imperfect consonances sound good, but have more complex frequency ratios. The minor 6, for instance, was at 128 to 81. Both major and minor thirds and sixths fall into this category. Dissonances include the major and minor seconds and sevenths, and anything that is augmented or diminished. I've included the perfect fourth here, and I'm going to ask you just to trust me for the time being. More often than not, the fourth is treated as a dissonance when it appears above a bass note, but it's understood as consonant if it appears, say, between the alto and tenor. We'll talk more about this problem as we get into part writing and counterpoint. Remember that consonance and dissonance are determined according to a variety of criteria: mathematical, perceptual, stylistic, and contextual. If you heard an interval consisting of 4 semitones, it's probably a major third, which is a consonance. It will, however, in isolation sound identical to a diminished fourth, which is considered a dissonance. The ear interprets both as a consonance, but if you look at them on paper, or understand how they behave in the context of a piece of music, those things can alter your perception. The composer Arnold Schoenberg often spoke of the emancipation of dissonance, arguing that there's no such thing as dissonance, it's all in how you think about it. Schoenberg and many other composers after 1900 freely used things like seconds and sevenths in the same way that Mozart used thirds and fifths. Schoenberg's music may sound unpleasant at first, but if you understand that he's treating all intervals equally as consonances, your appreciation of his music might change. By now, you should be able to invert intervals, you should be able to identify and write compound intervals, and you should have a little bit of background on things like consonance and dissonance and how we interpret those in terms of intervals. As usual, if you have any questions, post them to the discussion board on Canvas and feel free to answer your classmates' questions. And make sure to do the quiz before coming to class, and that will allow you to move on to the next lesson.